go ahead.
So there are broadly 3, 4 different kind of methods. One is the gradient, and then you try to improve the gradient in various ways. Second is the Newton's method and its variations, like we discussed. You have the Hessian inverse and all those. And then there are different approximations to Hessian inverse and how do you calculate that. And then there are methodologies which are totally derivative free, meaning you just calculate the function at different values. You don't calculate derivative ever and try to optimize. And then there are variations like even calculating the gradient method, calculating the gradient. If you have a lot of regressors, then it will become slow. So there is something called stochastic gradient.
He's going to teach that. I saw that topic as well too. Okay.
Yes.
What is the
So
difference?
that is stochastic gradient, you don't calculate the gradient exactly, you try to do some approximation of that.
Oh, okay.
So because the gradient calculation will be costly.
Gradient cost. Okay, got it. Okay, that makes sense. Okay, but overall, though, optimization will keep coming up in each of these, just different, the 3 different ways.
Just different, depending on the problem and depending on the difficulty in solving, we'll employ different methods.
Got it. Okay, I'm gonna send you, this is the only other topic that we have for now. This was the start of the classification with logistic regression. Classification problems. He started with the binary example of just classifying like cat dog pretty much, or 0, 1. And then he went into
That's what logistic is about, ultimately. Binary and then
because there's a
function
too, right? Yeah.
Yes. So
also on that list that I sent you, I think from like numbers 33 to 38 don't really make sense. Like the multi-class classification, one-hot encoding, logistic gradient descent, softmax function, decision rule, and then estimating the data parameters. So that list is a little tough.
all of these are related to the logistic regression. So you already understood the basic data that logistic regression is trying to base the model on. So we have the y variables, which are binary. It can be cat dog or from yes, no, or positive, negative kind of thing. And then we have x data, which we can assume to be continuous. If it's not continuous, if there are binary, then we can encode it to zeros and ones. If it is like a multi-class kind of thing, like red, green, blue kind of thing, we do that one-hot encoding where you have one column for red, one column for green, and then the blue is implied from the other two.
Yes.
So you are like quite comfortable with those, right?
And then that's the one where like red will be some probability, green will be some probability, blue will be some probability.
No. I'm not talking about the probability part. I'm talking about the regressor part. So if I have a regressor, which is like which can take only 3 different values, red, green, and blue. So, and I want to convert it to some continuous, like some numeric thing. If it were only 2 class, then I could do red and blue, let's say. Then I can say red is 0 and blue is 1.
Yeah.
But in 3, I cannot do 0, 1, and 2 because that will imply some relationship between them.
Oh.
So what I do is I will introduce 2 columns in the data. One column will be indicator of red, meaning it will be red, it will be 1 for red and 0 for others. One column will be indicator for blue, and then the green is implied from the other two, so we don't introduce another extra column for that.
So that's literally what one-hot encoding does.
This is what one-hot encoding does. So if you have a KY classification, KY like values for a regressor, then you introduce K minus 1 columns.
Got it. Okay. Got it.
Okay. So this is what we're doing. And then we want to predict Y given X. Now prediction for a binary thing, because our response is binary. We are not changing that. Since response is binary, we cannot, the prediction is not a number, it's a probability category.
Yes.
What chance we think of it being cat for this dog?
Yes.
It will be 99% or 99.9% of cat and 0.01% of dog or something like that.
Right.
So, and then because the response variable is binary, I think we discussed that generalized linear model tells us that the natural linkage is sigmoid.
Yes.
Okay. So the choice of sigmoid, like you can argue in very different ways why you are choosing the sigmoid function. The most easy way to justify it is that generalized GLM, the natural linkage for the Bernoulli is sigmoid.
Got it.
So the logic transformation, log of x over 1 minus x, log of t over 1 minus t is a linear function. Okay. And once we are doing that, after that, you can classify if you have a probability, if you need to convert the probability to a single prediction, meaning you have to tell me is it cat or dog, then I can do a threshold, like if it's probability of cat is more than 50%, then I will say cat. If it's less than 50%, I will say dog.
Yeah.
Now, in practice, this 50% may not be exactly 50%. You can put it somewhere else.
Right. Yeah. Weightage on.
Yes, and the reason being, like there is a type 1, type 2 error kind of thing here, right? Calling a cat a dog versus calling a dog a cat. These two need not be equally sensible, equally problematic for.
The example he gave was like spam and not spam.
Yes, exactly. That's a classic example. So if you miss a few emails because of spam versus if you actually click on a few spams, so which one is more important and so on.
Yeah.
So there are other examples like a criminal case, you are
Oh, yeah.
calling a person to be
Guilty.
actually criminal versus you are not calling a real criminal to be criminal. So that kind of stuff. So then you can decide the threshold and all that goes into it. Now, once you have this set up, then you can calculate the likelihood, which is basically the likelihood for Bernoulli, a bunch of data like this. And then you have to optimize this with respect to theta. Then what that means is typically you take the derivative, you take the log and set the derivative of logarithm to be 0. That gives you an equation to solve.
Sorry, I'm sorry, buddy. Hold on. There's so much going on in my head. Can you
Yeah, let's
explain
slow
that?
down here. So once we have let's say we know theta, or as a function of theta, we can write down the log likelihood. We can write down the likelihood, right?
Yes.
And now we want to choose theta, which will maximize this likelihood. That is the Emily concept.
Yes.
Okay. So to maximize the likelihood, algebraically, it is easier to take the log and maximize the log likelihood.
Yes.
So we write the log and then maximizing this, meaning setting the derivative to 0.
Yes.
Or you can think of maximizing this directly.
Yeah.
So, or minimizing this directly. So
With the
they
negative.
have removed the minus sign somewhere, I think.
Mm.
So then minimize this quantity.
Yeah, they did one
So
over
what
because
they are saying is that we can write this as some minimization problem of a summation of some quantity.
I'm sorry, buddy. Can you go up? Can you
Okay,
go?
there isn't much of. So we have a likelihood which
Wait,
has a formula.
I was confused how we put the parameters into this. How did we come up? How did we bring the thetas in? Because
Oh, so let me write down some of it. So, we have a y, which is response. Is this readable?
yes,
This is binary.
yes,
And we have some x data, which is my regressors.
yes,
And then we are predicting p of y equals 1 given x, which
yes.
is, let's say, h of x,
Okay.
or rather p of x. Okay.
Okay.
P can be 0 or 1. So predicting y equals 1 is enough, then y equals 0 will be 1 minus P of x.
Yes.
And then my logit linkage is telling me that log of P over 1 minus P is x, let's say beta plus, that's it.
Okay.
So instead of doing, so this is like the generalized linear model kind of concept. We are not modeling the P directly. We are taking a logit of that, and then we are doing a linear model on that.
Got it. Okay.
Okay? You can like ignore the plus epsilon for now, and just like a model like this.
Okay. Got it.
Okay. Now this will tell you that P will be 1 over 1 plus e power minus x beta. So x transpose beta. Okay, something like this.
Got it. Okay. Okay.
Okay.
Okay.
Okay. Now I have to calculate this for every data point. So every point will have an x and I will have a y. Okay. So my
Okay.
likelihood will be uh, product. What is the product? So it will be product of all the terms. So I have to vary from I equals 1 to n. And then if it is y is 1, then I have to take p. If it's y equals 0, then I have to take 1 minus p, right?
You're right. Yeah. Okay.
So it will be pi. So one way of writing that is pi power yi. Sorry, pi power y I and 1 minus pi power 1 minus yi.
Bernoulli. Okay.
Now, this is complicated way of writing that if y is 1, then I take pi. If is y is 0, I
Oh,
take 1
because then
minus
that
pi.
cancels out. The other one cancels out. Right. Okay.
Okay. And then you can substitute the p in this, and then you get the formula for likelihood.
Oh, okay.
Okay.
You substitute the P into the likelihood formula, and then you
Yes.
have a likelihood formula.
Formula for the likelihood.
Yeah, using your regressors and your parameters.
Yes. Now we have to solve for beta. Then what they do is take the log likelihood and say that we want to maximize this with respect to beta.
Got it. Okay, very cool. Very
And
cool.
that's a maximization problem. So people can use gradient descent in that.
Yes.
Okay.
Why would we not do ML? Wait, is MLE and gradient descent, are they linked together then?
Yes. MLE is what we want to do. Gradient descent is how we are doing it.
Okay.
MLE is just saying that we want to maximize the likelihood.
And then you take the derivative, set it equal to zero. Got
Yeah.
it.
That is.
Likelihood. Oh my gosh.
Gradient descent is a way of doing it.
Yes, duh. Yes, that was the steps 3 and 4 on MLE. Okay.
Okay.
But we're
So that's
solving for, what are we solving for in this? We are solving for, no, we have P. We're solving for
we're
your,
solving for beta
we're solving for parameters. Yes. Okay. Yes. Okay.
parameters.
Yes.
Like in your case, it is notation it has theta.
Yes. Got it.
Okay. And they have written it's slightly fancy way that it's you are minimizing 1 by n summation some loss function. That loss function is a formula like this. Okay, and then you apply the formula for gradient descent, you get this, and then you explain all those things, and then you get a you have to show that this is actually a convex problem, so that the local maxima will be global maximum.
Okay.
So there is some algebra to that, which I'm not going to. And the algebra is basically that the second derivative, the Laplacian term del square will be positive semi-direct.
Why are we taking the second derivative of the loss function?
Because we discussed this little bit more. Yeah.
Can we relate
So
it back to this?
yeah, so we are solving this thing, right? If the first derivative is zero and second derivative is positive, we
Yes.
know that the point is local minima.
Okay.
So second derivative in higher dimension is the gradient second derivative, which is the Hessian.
Okay. Can you go back to the other page? Sorry.
Yes.
And then
So you can see this del theta I, del theta j. This is the second derivative.
got it. Okay. Got it.
Okay. So that is the problem.
Okay.
Okay.
Yes.
And that basically tells us that we are solving a convex problem. So gradient descent is a good thing to do.
We can do
Okay.
gradient.
And then there is another section for multi-class. So multi-class is basically try to generalize from two-way classification to multi-way classification. And this is the standard trick that you take. So we had earlier 1 over 1 plus e power minus something, right? So
Yes.
you take a bunch of those and then you have e power z1 by sum of all the e power zi
For each class.
for each class.
What
And here
is
the class is on the response part.
what is Z?
Z is your classification score.
Classification score. Okay. Okay.
So
So that's what.
basically, this is the score given to each class. So this is like the part of the prediction.
Wait, I thought
And
the
that
score was theta. I mean the sigma. What is sigma then?
sigma is the corresponding probability.
So there's a score and then there's a corresponding probability
Yes.
based on that score
Yes.
then. And how
I'll
do we
explain what is going on there. So here, so we had this probability p, right? And then we said log of p over 1 minus p equals x beta.
yes.
So let's break into two steps. So say log of p over 1 minus p equals z and z equals x plus beta. That is what they're doing. Okay. So from the x, if you know the beta, then you calculate the z. And from the z, you calculate the p. Two steps.
Oh, but the
Okay.
formula is going to be different based on multi-class then.
Yes. So
Because
those
it's not,
formulas, if you put k equals 2 class there, you will get this.
yes, exactly. You'll if you put two
So
because then
now,
it'll be P, it'll end up being P over 1 minus P log. Yeah.
so
That
that
makes
is what they're okay.
got it. That makes sense.
So this is the corresponding formula for multi-class.
And then that's sigma. Okay.
And the sigma is the corresponding thing for probability.
And you'll end up
Uh,
with a vector, right? You'll end up with a
vector
vector
of probability.
with the
With the
variety.
idea that all the probabilities should be non-negative and this should add up to 1 across
Yes.
all the classes.
Yes. Okay.
Okay. And between two classes, so let's say I have cat, dog, and elephant. So between cat and dog, it is kind of a sigmoid. Between dog and elephant, it is sigmoid. And between cat and elephant, it's also kind of a sigmoid.
I was just wondering that, Sujay, because on the sigmoid function, it does only indicate that there's two like how
Yes.
can I visually
No way
see
to,
this?
yes, do a sigmoid in between three. So
Yeah,
that's why this is a way to do that such that between any two, it is like a sigmoid. But overall, it's a three-way classification.
between two classes, there's a sigmoid. Okay, but then there's a three-way
There's
classification.
an implied sigmoid from there.
Got it.
Okay. And earlier we were fitting only a single beta or theta parameter. Now we'll fit one theta for every class.
For each class, then. Yeah.
So, so you can think of it this way. So earlier we needed to classify between cat and dog. So we need a theta that will separate the cat and the dog.
Yes.
Okay.
Yes.
Or you can say this way that, okay, so cat minus dog will get a theta in some sense. Like the separation between the cat and the dog will get a theta.
Oh, right. Yeah, yeah, yeah.
Okay.
Okay.
Instead of doing that, what you can do is you can give a theta to cat and theta to dog, and the difference of those two only matter.
Got it. Okay.
Okay. Now we give a score to every one of them. So cat will get theta 1, dog will get theta 2, elephant will get theta 3. And then between dog and elephant, the theta 2 minus theta 3 is what is going to matter.
Ah, okay. Okay.
So that
Yes.
will tell us how the classification works. So there is a sigmoid between the dog and elephant even now.
That makes because that there's a theta difference then.
Yeah. As opposed to this, what we could have done is we could have given a theta to cat versus dog, one to dog versus elephant, and one to elephant versus cat.
Right.
That is also like you get three. But imagine if you want to do a 10-way classification, and if you want to do all pairwise, you need 45 thetas.
Yeah.
But it's much easier to give a theta to every animal, and then classification is always you take the difference between the two animals. So that's why this idea is good.
Got it.
So that's basically it. And then you write down the whole maximization problem, and then you can prove that this is a convex problem. So you can do gradient descent. And in practice, you will leave it to computer to do the rest.
Communication there.
Won't do it by hand.
What the other one that he gave? Oh, that one, the function that he wrote there, the one fancy one. That one he said was
That is like indicator. So this is basically an indicator of yi equals k. If y is k, this thing is 1, otherwise it's 0.
got it. Yeah. So that'll
So
be
this
the
is again a
indicator.
generalization of that this thing. We
Yeah.
are doing power
Because
yi and then 1 minus
it
yi, right?
cancels that
So this
off.
is like a
Yeah.
general version of it.
That off then. Okay.
You have a ky version of this. So there is a double product, that's why.
Yeah. Okay. That's a
So
good.
that's basically how this works.
This actually makes conceptual sense, Ajay. I'm actually understanding all of the concepts here. The math I'm a little shaky on. I might have to review some of them.
Just go through line by line slowly
Yeah.
and
Yeah.
go through. I hope you understand all the notations by now, and I think
Yes, I
you
understand. I actually know all the notations by now. No question. If I
and
do
you
know the
understand all
notation,
the major concepts by now. That's what my aim was.
yes, yes. If I don't know the notation, I'll definitely ask. But so far, I understand all of the notation around here too.
And I have explained you all the major concepts. So
Yes.
now you can go through line by line of how they have written it and what is going on.
Sometimes I've seen beta, sometimes I've seen theta. That's why sometimes I get confused with those two.
It's
But I
like
know
so okay. The thing is, when
abstract,
people talk about general modeling, they use theta,
right?
but when they do linear model, they use beta.
Makes sense. Okay.
I also keep interchanging, like it doesn't matter much.
Okay. 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 What time is it? 12.
11:30. We still have time. Anything else you want to cover?
These are all of the lectures he's given. He's going at a pretty good rate. He's only given us one homework assignment also, Sujay. So I haven't had any. I did pretty well on that homework. It was pretty much a review. So I think the homework he's going to give next is going to be like covering all the regressions, right? So linear regression, the ridge regression. He didn't do lasso in class. I know we did lasso here, but that's when he
Yeah,
didn't.
they are very similar and related. So I wanted to like cover both and do a contour.
Yeah.
That makes sense.
Okay, this might be a good pause point then, Sujay, so we
Okay.
can call it 2 hours then for today. I
Okay.
think this is a good
If
stopping.
you want, I can go through something else if you have
Yeah,
time.
is there, I'm trying to see what else is there. Let me see what else I have, buddy. Hold on. Um, can we maybe start reading through the paper? Is that fine?
Yeah, that's a good idea.
Let me stop. I'll stop recording.